This is your presenter, Asloob Mudassar, and I am presenting slide number 18G of the course on atomic and molecular physics. In the today's lecture, I shall be covering rotational and vibrational diatomic molecules, Born-Oppenheimer approximation, the rigid rotor. This is the seventh lecture of the series on molecular physics. To understand this lecture completely, you should go through previous 6 lectures from 18A to 18F. Rotation and vibration of diatomic molecules. You see that in the previous lecture, that is up to the lecture number 6, I have ignored the rotation and vibration of the diatomic molecules. Now I am going to include the rotation and vibration in a diatomic molecule model. We have discussed rigid molecules, and now we are going to include rotation and vibration of diatomic molecules. This requires to take into account the kinetic energy of the nuclei in the Schrödinger equation. So you see that we have to include the kinetic energy of the nuclei into the Schrödinger equation, which is H operator operating on the wave function psi is equal to E psi, where E is the eigenvalue of the equation. The Hamiltonian of the problem will take the following form. So you see that this is the Hamiltonian of the problem, minus h bar square over 2, and summation from k is equal to 1 to k to 2, and 1 over mk multiplied by the del k square, and then minus h bar square over 2 me, summation over I is equal to 1 to n, this is del I square, and then plus e square over 4 pi epsilon naught, and within the square bracket I have z1 z2 over r plus summation over ij, and the term is 1 over rij minus summation over I, and the parenthesis containing 1 over ri1 plus 1 over ri2. This can simply be abbreviated as H operator is equal to kinetic energy of the nuclei, E kin of nuclei plus kinetic energy of the electronic state, which is the E kinetic, EL stands for the electronic state, and then plus E pot of 0, where E pot stands for the potential energy of the system. So you see that I can combine some terms as Tk, that is the kinetic energy terms. So for example, the first two terms can be combined as the kinetic energy terms, and the last term can be combined as the H0 operator. And you see that here I am going to explain these terms. In equation number 109, the first term is the kinetic energy of the nuclei. So this term is actually the kinetic energy of the nuclei. The second term is the kinetic energy of the electron. The third term is the potential energy of the nuclear repulsion, that is this one, Z1, Z2 over R. This is the term that corresponds to the potential energy of the nuclear repulsion. The fourth term, that is this one, is the potential energy of the electron repulsion. Due to, you can see a positive sign stands for the repulsion, and then there is a negative sign, and the last term is the potential energy due to the attraction between the electrons and the nuclei. For example, Ri1, so I stand for the ith electron. So Ri1 is actually the distance of the ith electron from the nucleus 1. And Ri2 means that this will represent the distance of the ith electron from the nucleus 2. And this Rij means that it's the separation between the ith electron and the jth electron. So Z1 and Z2 are actually the atomic number of the nucleus 1 and the nucleus 2 divided by the capital R, which is the separation between the two nuclei. And the first term is what? And Mk, capital M with the K as a subscript. This stands for the mass of the nucleus A. And Me is the mass of the electron. Small me is the mass of the electron. So let me read the paragraph. In equation number 18.109, the first term is the kinetic energy of the nuclei. Second term is the kinetic energy of the electrons. Third term is the potential energy of the nuclear repulsion. Fourth term is the potential energy of the electron repulsion. And the last term is the potential energy due to the attraction between the electrons and the nuclei. Now let's talk about the Born-Oppenheimer approximation. Nuclei being heavier move slower than electrons. Electrons adjust their positions quickly when the nuclei move or acquire new nuclear configuration. The electronic wave function represented by psi of R and capital R depends on capital R, but barely affected by the velocity of the moving nuclei. So as I said earlier that the nuclei being heavier particles than much heavier than that of the electrons, the velocity of the moving nuclei will not affect much the electronic wave function psi of R, comma capital R. The kinetic energy of the nuclear motion is E kinetic is equal to half capital M into Vi square, where capital M is the mass of the nucleus and capital V is actually the velocity of the nucleus. You may treat this capital M as the reduced mass of the problem. The total Hamiltonian H can then be written as, so from the previous equation, I can write capital H, the Hamiltonian of the problem, to be equal to H naught plus Tk, where H naught is the Hamiltonian of the rigid molecule. You see that I have discussed the rigid molecules up to lecture number 6, and this is lecture number 7. So H naught is the Hamiltonian of the rigid molecule. Tk is the kinetic energy of the nuclei. Tk will be treated as a small perturbation to H. So Tk may be considered as a small perturbation to the Hamiltonian H. The total wave function can then be written as psi of Ri comma Rk is equal to chi of Rk into phi of Ri and Rk, where I is the distance of the ith electron from the center of mass and Rk is the separation between the nuclei, between the two nuclei at the electronic, when they are at electronic separation K. So you see that here I have splitted the wave function of the system into two parts, chi of Rk and phi of Ri and Rk, which I am going to explain in the next paragraph. Chi of Rk is the molecular wave function. R of k gives the position of the nuclei and is treated as a fixed parameter. Phi of Rk is the electronic wave function of the rigid molecule. Ri gives the electron coordinates and is a variable quantity because the electrons are in motions. The nuclear and electronic motions are independent and any coupling between them can be neglected. That's why they have been separated into two parts, chi of Rk and phi of Rk, because there is no interaction between the two parts and they can be treated as independent quantities. So the nuclear and electronic motions and their corresponding wave functions are independent and any coupling between them can be neglected. So capital chi is the molecular wave function as a function of Rk, where k may be where k is the kth electronic state, will give you the position of the nuclei, and Rk is the separation between the two nuclei at its kth electronic state, and Rk could be treated as a fixed parameter, and phi, which is the function of Ri and Rk, is the electronic wave function of the rigid molecule. And you know that the rigid molecule, we have already discussed the rigid molecule up to lecture number 6. The total energy E is the sum of energy En superscript El as a function of R of the rigid molecule. So the total energy E is the sum of energy E and EL as a function of R of the rigid molecule in the nth electronic state. So N stands for the nth electronic state, represented by the potential curve shown below. And the kinetic energy term is actually will consist of two parts, that is vibrational energy plus the rotational energy of the molecule. These two together will be combined into the kinetic energy of the nuclei. The total energy is independent of the capital R. So the total energy of the system will not depend upon the value of R between the two nuclei. So now let me show you the plot of En of L as a function of R. So this is the potential energy curve corresponding to the nth electronic state. And you see that the potential energy curve has a dip, and the minimum value at which the energy at which the curve cuts the horizontal axis is RE, where RE is the equilibrium separation between the two nuclei. And then of course you see that the red curve increases as the separation between R increases, and ultimately it will reach a value which is the total energy of the system, which is constant. And E, this horizontal line in the, which cuts the curve, vibrational curve E, which cuts the curve En of L as a function of R at a fixed value. This horizontal value will give you the total energy E, which is equal to the En of El at a value of R plus vibrational energy of the molecule plus the rotational energy of the molecule. And at the bottom of this curve, which is the red curve, you can see that there is a zero energy, 0 point energy. So this is the 0 point energy, that is the minimum energy that the molecule will have even at absolute temperature, at zero absolute temperature. So you see that here I have shown the two separations, that is the dissociation energy dE of the non-rigid molecule. Since here we are talking about the non-rigid molecule, and here dE, which has been specified by the arrow from the dotted line and to the 0 point energy, this value is the dissociation energy. That is, if you provide this much energy to the molecule will dissociate. So that is why it is referred to as the dissociation energy of the molecule. And next you see that I have shown the binding energy of the rigid molecule starting from the minimum value given by the red curve at a distance of RE. So from this value to the dotted line curve will give you the binding energy of the rigid molecule. Because if you supply this much energy to the molecule will be split into its atomic parts. And you know that this dotted black line is actually the line beyond which if the curve is below this one, the molecule will remain in the bound state. But if the energy of the molecule exceeds this dotted black horizontal line, it means that the molecule will split into its atomic constituents. The energy ENEL as a function of R of the rigid molecule, and the total energy E of a non-rigid vibrating and rotational molecule. So you see that here the total energy includes both the energy of the rigid molecule plus the energy due to vibrational state of the molecule and due to the rotation of the molecule. These three quantities will form the total energy of the molecule, whereas En of El as a function of R represents the energy of the molecule when it is purely in the rigid state. The approximation which neglects the interaction between nuclear and electron motion is called Born-Oppenheimer approximation. So you see that since we are applying this condition, it means that we are neglecting any interaction between the nuclear and the electron motion. The total wave function can be written as the product of electronic wave function, which describes the molecule with clamped nuclei. That is the rigid model of the molecule, and the wave function describing the vibration of the nuclei and the rotation of the whole molecule. So you see that our total wave function can be written as the product of the electronic wave function, which describes the molecule with clamped nuclei, and the wave function describing the vibration of the nuclei and the rotation of the whole molecule. This means that the vibration of the nuclei does not change the electronic state. So you see that here we can consider the electronic state to be independent of the vibrational state of the molecule. That is when the vibration, when the molecule vibrates, it will not affect the electronic state of the molecule. The Born-Oppenheimer approximation breaks down for higher electronic states where vibration can induce a coupling between different electronic states. This means that the vibrating nuclei do no longer move in a well-defined potential of a single electronic state, but changes the electronic configuration during the vibration. So you see that when we remain under the approximation of Born-Oppenheimer, then of course there will be no coupling between the electronic and the nuclear states. That is, the vibrational states will be independent of the electronic states. But you know that at very higher electronic states, the vibrations can induce, that is, the vibration of the molecule can induce coupling between different electronic states. That is, at very high electronic states, the Born approximation will be broken down, and the coupling between the vibrational states and the electronic states will start. This means that the vibrating nuclei do no longer move in a well-defined potential of a single electronic state, but changes the electronic configuration during the vibration. Actually, under the Born-Oppenheimer approximation, this electronic state shown by the red curve will contain many horizontal lines within this curve representing the vibrational levels. Operating the wave function of equation number 112 by the Hamiltonian operator shown in equation number 110 or 109, the following two equations are obtained. So let me show you equation number 112 first. This is a wave function 112, and this will be operated by the Hamiltonian shown in equation number 110 or 109. And once after the operation, we shall get these two equations. You can work out yourself that these two equations are correct. So you see that H naught operator operating on phi n of EL, which is a function of R and RK, and on the right hand side you have En of 0, which is the eigenstate energy, and then again the wave function phi n of phi n EL at values as a function of R and RK. So you see that when you use equation number 113 in one of the previous equation, you will obtain equation number 114. So you can see that I have Tk operator plus the energy En as of zeroth order energy En, and then these two will operate on the wave function x and m as a function of R, and you will again get the zeroth order energy En of 0 and then x and m of R. So you see that these two equations can be obtained very easily, as I have stated, that you put the wave function, that you operate the wave function given in equation number 112 and operate this wave function either by the Hamiltonian shown in equation number 110 or shown in equation number 119. And there you can very easily find out these two equations. So you see that in these two equations we have the separated the states with the wave function phi and wave function chi. So one equation contains wave function phi on both sides, that is in equation number 113, and equation number 114 contains the two wave function chi and m as a function of r. So we can solve these two wave equations separately. And you know that these two equations have been written under the Born-Oppenheimer approximation. Because we are assuming that the Born-Oppenheimer approximation holds, and under that condition we have written these two equations. The first equation describes the electronic wave function phi of the rigid molecule in the electronic state, determined by the three parameters n, capital L, and capital lambda, where capital L is the total angular momentum of the molecule and capital lambda is actually the projection of capital L on the horizontal axis or the internuclear axis between the two nuclei. And En of 0 is the total electronic energy of this state without the kinetic energy Tk of the nuclei. So excluding the value of the total energy Tk, total kinetic energy Tk of the nuclei, I have obtained the electronic energy En of 0 as the total electronic energy of the electronic state. And of course, the electronic state is determined by three parameters n, capital L, and capital lambda. And phi is actually the electronic wave function of the system. The second equation contains the kinetic energy Tk of the nuclei and determines the motion of the nuclei in the potential defined by. So En of 0 is equal to the average kinetic energy of the electronic system plus E pod, which is the potential energy of the system as a function of Ri and Rk. This is the full representation of the En of 0, which is the total electronic wave function composed of the average kinetic energy of the electrons plus the potential energy of the system. This consists of time average of kinetic energy of the electrons and the total potential energy of the electron and nuclei. That's why I have said that this is the potential energy of the system, which means that the potential energy containing electron and nuclei. The total energy of the non-rigid molecule is the sum of the kinetic energy of the nuclei and the total energy of the rigid molecule as given by E of Nk. You remember that I am writing this expression for the non-rigid molecule. En of k is equal to E kinetic of nuclei plus En of 0. And En of 0 is the total electronic energy of the state, and this is what I have defined En of 0 in equation number 115. And equation number 116 gives you the energy of the non-rigid molecule. En of k is the energy of the non-rigid molecule, which is the sum of the kinetic energy of the nuclei plus the total energy of the electronic states under rigid molecule condition. Now you see that I have the two differential equations or I have the two equations. For example, these are the two Schrödinger equation wave equations, and I can solve these Schrödinger wave equations separately by specifying the value of the Hamiltonian H0 operator in the form of the operator and Tk as an operator. These values have been specified over here in equation number 117 and 118. And this is the value of the Hamiltonian operator H0, which contains the kinetic energy of the nuclear part, which is minus h bar square divided by 2ma. Here I have used the triangular A, but this triangular will be related later on to the del square operator, and plus minus h bar square over 2mb, where ma is the mass of the nucleus A and mb is the mass of the nucleus B. And again I have used the function triangle B. In principle, this triangle B will later on be connected with the del square operator. And this E part of n as a function of r is actually the potential energy of the system as a function of rk. And you know that here the wave function is chi nm as a function of rk. And on the right hand side, I have the eigen energy of the system enm. And you know that enm has been defined in equation number 116 and then multiplied by the wave function chi nm as a function of rk. So you see that this equation reduces to the simplified version given in equation number 18 in the center of a mass system coordinates. And in this coordinates I have minus h bar square over 2m, and then the triangle function, which will be later on related with the del square operator. This capital M is now the reduced mass of the system. That is due to the two nuclei, we have written the reduced mass capital M. And then this is the potential energy of the system. And then the wave function chi nm. And on the right hand side, I have the eigen energy E and M multiplied the wave function chi nm. You see that actually I am working out on this equation, which is equation number 114. So from equation number 114, by using the explicit form of the H0 operator, the TK operator, and then using the value of the TK operator. This is not the H0 operator, but it is the value of the TK operator. That is the kinetic energy operator. So please make a correction. It is not H0, but it is the kinetic energy operator. And in the center of mass coordinates, this will reduce to this quantity in the square bracket. So in the square bracket, I have the kinetic energy operator plus the potential energy of the system. And here the capital M is the reduced mass, which is given by M is equal to MA plus MB divided by MA plus MB. And this M is the reduced mass of the two nuclei, and the index M gives the mth quantum state of the nuclear movement, that is the vibrational and rotational states. So you see that here M, you can see I have written M as a subscript with the wave function chi n comma m, and that M is actually the gives you the mth quantum states of the nuclear movement, that is the mth state of the vibrational and rotational states. The potential energy of the nuclear motion in the electronic state determined by n capital L capital lambda depends only on the nuclear distance capital R and not on the angles theta and phi. That is, it is independent of the orientation of the molecule in space. So our electronic state will not depend upon the value of theta and phi, that is independent of the orientation of the molecule in space. It is spherically symmetric. The wave function chi as a function of capital R, theta, phi, however, may still depend on all the three variables R, theta, and phi. But you know that when we are talking about the electronic state will depend only on the nuclear separation capital R and will be independent of theta and phi, whereas the wave function chi will still depend upon three variables capital R, theta and phi. In equation number 118, this equation may be treated as a Schrodinger equation of the hydrogen atom because of the spherically symmetric potential. This is equation 118. The equation differs only in the radial part, of the potential. The wave function will be written as the radial part and the angular part. So this is the wave function chi as a function of r, theta and phi. This can be written as capital S of r, that is the radial part wave function, and the azimuthal part of the wave function written as y of theta and phi. SR of S S of capital R depends on the radial form of the potential. The spherical surface harmonics y of theta and phi are the solutions for all spherically symmetric potentials. Inserting equation number 120 into equation number 118 will give us, that is, I am using equation number 120 into equation number 118, then I obtain the following equations. So this is the first equation in the radial form, and the second equation is in the azimuthal form containing the variables theta and phi. And you know that this transformation is very simple. If you want to know the detail of this transformation, you can consult the hydrogen part of the atomic physics problem. So in the atomic physics part of the hydrogen atom, you can find out these two equations in which we have a radial part separated from the azimuthal and azimuthal part. So the first equation in the radial part, this describes the vibration of the diatomic molecule. And the second one describes the rotation of the diatomic molecule. Remember that the function chi, that the wave function chi is actually the nuclear wave function. And now we have separated that nuclear wave function into two parts. One represents the vibrational motion of the diatomic molecule, that is the radial part, and the azimuthal part of the wave function of the differential equation will represent the rotation of the diatomic molecule. The rigid rotor. A diatomic molecule can rotate around any axis through the center of mass, perpendicular to the internuclear axis. You see that when you join the two nuclei, you have the internuclear axis, and there is a center which is called the center of mass, and through that center of mass you have an axis which is perpendicular to the nuclear axis through its center of mass. So a diatomic molecule can rotate around an axis through the center of mass, which is perpendicular to the internuclear axis, with the angular frequency omega, and with a rotational energy E rot. So E rot stands for the rotational energy of the molecule, and this is simply given by E rot is equal to half I omega square. And you can replace this omega square, and you can write this quantity in terms of E rotational is equal to J square over 2I. Because you can multiply this equation with I, you can also divide this equation with I. So you have I square omega square, and you know that the value of J is equal to I omega. So since you have I square omega square, you have J square on the right hand side, where this I, which is the moment of inertia, is simply given by I is equal to MARA square plus MBRB square. And if you represent this equation in terms of the reduced mass of the problem, and from the geometry of the problem given on the next page, you can immediately write the value of I to be equal to M times R square. where m is the reduced mass of the problem, and the reduced mass of the two nuclei has been defined earlier. Capital I is the moment of inertia of the molecule with respect to the rotational axis, and J mod is equal to I times omega is the rotational angular momentum. So capital J mod is actually the magnitude of the rotational angular momentum. So J is the rotational quantum number, which is related to the physical parameters under the condition that J mod is equal to I times omega. Since J is a vector quantity, I have written only its magnitude over here. For rotation around internuclear axis, the contribution of the nuclei to the moment of inertia is vanishingly small because they lie on this axis. The contribution of the electron shell is also small because of the small electron mass. Therefore, the rotational energy for a rotation around this axis is very large and cannot be excited at thermal energies. So you see that here the point that I want to make is that the thermal energy of the system in which the molecules are placed, the thermal energies will not be enough to excite the rotational energy of the molecule, because the magnitude of the thermal energies are far smaller than the energy required for the rotation of the molecule. So let me read this paragraph once again. For rotation around the internuclear axis, the contribution of the nuclei to the moment of inertia is vanishingly small because they lie on this axis. The contribution of the electron shell is also small because of the small electron mass. Therefore, the rotational energy for a rotation around this axis is very large and cannot be excited at thermal energies. The electronic contribution has only to be taken into account for electronic states. The electronic contribution has only to be taken into account for electronic states when the value of capital lambda is greater than 0. That is the projection of the total angular momentum capital L on the internuclear axis, which we call as capital lambda, should be greater than 0 and is then added to the electronic energy. This will be discussed later on in the next few lectures. Rotational energies of a molecule in its equilibrium position with an internuclear distance Re are given by. So this is the formula for the rotational energy of the molecule. E rot is equal to absolute square of J divided by 2 into capital M into capital Re squared, which is equal to J into J plus 1 times H bar square divided by 2 times capital M times capital Re square. The diagram of a diatomic molecule as a rigid rotor is shown on the next page. So this is the diagram of a diatomic molecule as a rigid rotor. You can see that I have two nuclei with masses Ma and Mb respectively. The nuclear mass B shown in this diagram is heavier than the mass than the nuclear mass A, and A and B represents two nuclei. Now capital S is the center of mass of the two nuclei, and the axis that is blue shown in blue passing perpendicular to the center of mass and is also perpendicular to the AB axis is actually the axis through the center of mass, and the molecule as a rigid rotator will rotate about this axis And this axis is at a distance RA from the nucleus A and RB from the nucleus B. The nucleus A and the nucleus B are separated by the distance capital R. Here you know that J and J plus 1 are the two consecutive rotational levels. So J may be referred to as the rotational quantum number, and two consecutive rotational states or levels will be represented by J and J plus 1. The energy separation between the rotational levels J and J plus 1 is given, which increases linearly with J as shown on the diagram on the next page. So here is the formula that I am writing: delta E rot, that is the energy separation between two consecutive rotational level delta E rot, is equal to the rotational energy at a J plus 1 minus the rotational energy at a value of J. The separation between two is J plus 1 multiplied by H bar square divided by capital M into RE square. For capital R to be fixed, S of R is also fixed. The first term in equation number 121 is 0, which implies that the second term is also 0 because the sum of the two terms is 0. The kinetic energy of a rigid molecule which does not vibrate is E kinetic is equal to E rotational is equal to E minus E potential. So from the total energy of the molecule, if you subtract the potential energy, you will get E kinetic energy is equal to E rotational. So the kinetic energy of a rigid molecule which does not vibrate. So you see that if you ignore the vibration, then the kinetic energy of the molecule will be equal to the rotational energy will be equal to the total energy subtracted from it, the potential energy of the system, where E is the total energy. The second term is in the square bracket, then reduces to equation number 125. So let's consider equation number 121. You see that this is the equation 121. And about this equation, what we have, so you can notice these terms. This is the radial equation representing U, which describes the vibration of the diatomic molecules. You can notice different terms over here. There are three terms in the square bracket. And there is one term outside this square bracket. And about this term, I have stated this paragraph that for fixed R, S of R is also fixed. So due to S of R being fixed, some derivatives will be equal to 0. The first term in equation number 121 is 0, which implies that the second term is also 0 because the sum of the two terms is 0. And the kinetic energy of a rigid molecule which does not vibrate is E kinetic is equal to E rotational is equal to E minus E pot, where E is the total energy. The second term in the square bracket then reduces to equation 125. That is this equation, because the rest of the equations will be equal to 0. You know that when capital R is fixed, capital S is also fixed. The derivative of the derivative is 0. So this term vanishes. So when this term is equal to 0, then of course the rest of these terms will be equal to 0. So when R is fixed, S of R is fixed, the first term in equation number 121 is 0, which implies that the second term is also 0. because the sum of the two terms is 0. The kinetic energy of the rigid rotor, which does not vibrate, you know that here we have put the condition that which the rigid rotor which does not vibrate, and if it will not vibrate, then of course the J value will be equal to 0. And when capital J is equal to 0, then the kinetic energy of the molecule will be equal to the rotational energy. Then the kinetic energy of the molecule will be equal to capital E minus E pot, where the potential energy. So you subtract the potential energy of the system from the total energy, you get the kinetic energy. And you know that this will hold under the condition that we neglect the vibration of the molecule. That is, we set the total value of capital J, that is the angular momentum or rotational angular momentum J will be set equal to 0. The second term in the square bracket then reduces to. So you see that when you set the second term in the bracket equal to 0, you will get the term equal to by equation number 125, in which you have E rotational equal to this value. You see that in the previous equation, I have the rotational energy of the molecule given by this equation. That is equation number 125. And there you see that E potential energy will vary linearly with the principal quantum number J. If it does so, let me show you the plot of this curve, this equation also. So you see that I am not plotting that equation, but in principle I am plotting delta E rotational. So you know that delta E rotational depends linearly on the value of capital J. So it varies linearly with the value of J. That is the separation between the consecutive level between the levels, which depends upon the value. That is, if the separation between the rotational level is J, then the energy of the rotational level will depends upon the value of J. So the greater the value of J, the greater would be the value of the separation between the two rotational levels, which are separated by the value J. And this is actually shown over here. You can see that E rotational plot, which is equal to J plus 1 times H bar square over capital M and R E square, has been shown over here as a function of R, as a function of J. So as the value of J will increase, the value of E rotational will also increase. That is, the separation between the two rotational levels will also increase. And here I have shown angle as the angle of this slope, and the tan of alpha is proportional to delta E rotational divided by J plus 1. And if you put the value of E rotational in this equation over here, you will get H bar square over capital M times R E square. So the slope, so tan of alpha will be proportional to H bar square over capital M and R E square. And you know that on the left I have shown rotational levels. These are the rotational levels. And the new one is the frequency. If you provide a frequency, if you provide a light for absorption in the molecule at a frequency nu1, it will be absorbed and it will reach the second level. And at the second level, if you provide a frequency nu2, it will reach to the third level. And if you provide a light with a frequency nu3, the light will be absorbed in this region and it will reach to this level. And similarly, nu4, that is the frequency equal to nu4, will raise the level from this rotational level to the higher level. So f of j is actually the distribution of the rotational levels. And you know that different frequencies can be used to excite different rotational levels. The spectrum of the rotational level, which will emerge out with the de-excitation from this under these rotational levels, is given on the right hand side as intensity of intensity of the frequencies is plotted over here, and the rotational frequencies are plotting on the horizontal axis with the frequency, rotational frequency nu1, nu2, nu3 and nu4. And you know that these will fall at these places in the rotational spectrum. So energy levels of the rigid molecule are shown on the left as a staircase of rotational levels. B will give you the separation of delta rotation, which is E rotation at a value of j plus 1 minus E rotation at a value of j. This has been plotted in part number B, and C shows you the schematic of the rotational spectrum. So this is the rotational spectrum which will be obtained under the transitions from these rotational levels indicated by f of j. So these rotational levels, when D excited, will give you the spectrum with the intensities I of nu, and plotted with the frequencies nu rotational, and 4 frequencies at different locations will be emitted, and their proportional intensities are also shown. In spectroscopy, rotational terms designated by f of j are used instead of equation number 125. So equation number 125 can be rewritten as f of j is equal to E of j divided by hc. So f rotation, you can also put a subscript f rotation of j is equal to j into j plus 1 multiplied by h bar square divided by 2 hc into m into re square. And if you can write it in abbreviation as be times j into j plus 1, where be, which is equal to h bar divided by 4 pi c into capital M into re square is actually be is actually the rotational constant. So now I have represented the function f rotational as a function of j equal to be times j into j plus 1. Rotational energies fall in the range given below. E rotational varies from 10 to the power minus 6 to 10 to the power minus 12 minus 2 times j into j plus 1, and these are in electron volts. Classical relationship between rotational angular momentum j, circular frequency omega, which is equal to 2 pi nu, and the moment of inertia I is given by, so j in vectorial form is equal to omega in vectorial form multiplied by the moment of inertia I. So this is the rotational and the classical relationship between j and I. And you know that since j is a rotational quantum number, the magnitude of j will be given by the square root of j into j plus 1, and outside this one I have h bar. And magnitude of omega is equal to 2 pi nu. The rotational period is given by T rotational is equal to 1 over nu, or T rotational is equal to 2 pi I divided by h bar and divided by the square root of j into j plus 1. Depending on the value of BE, T rotational varies from 10 to the power minus 14 second to 10 to the power minus 10 second. For EE is equal to 1 centimeter inverse, one gets T rotational equal to 1.6 into 10 to the power minus 11 divided by the square root of j into j plus 1. This is shown in seconds. V rotational as a function of j is equal to E as a function of j plus 1 minus E as a function of j divided by h. So if E at two different values in a rotational system is known, you can find very easily the rotational frequency. So rotational frequency as a function of j can simply be written as 2 multiplied by rotational constant Be multiplied by j plus 1. Between two consecutive rotational levels, the spectral range is found as nu varies from 10 to the power 9 to 10 to the power 13 hertz, that is in the gigahertz to terahertz range. And with the corresponding wavelength range is lambda from 10 to the power minus 5 to 10 to the power minus 1 meter. This is the microwave region. That is the rotational levels normally gives you the energies in the range of gigahertz to terahertz, and the wavelength ranges in the microwave region. Only molecules with permanent electric dipole moment. Only molecules with permanent electric dipole moment can absorb or emit radiation on rotational transitions, except for weak quadrupole transitions. Therefore, homonuclear diatomic molecules show no rotational absorption or emission spectra. So you see that here we have established that the homonuclear diatomic molecules will show no rotational absorption or emission spectra. So you see that here I have explained a little bit about the vibrational levels in an atom in a molecular system, and also the rotational levels. When we have considered the non-rigid model of the molecules. And under the non-rigid molecules of under the non-rigid approximation of molecules, we have described the vibrational and the rotational wave functions and the energies of the rotational and vibrational molecules under different conditions, and their formulas have been given, and their values of energies and wavelength ranges have been defined. So this is the end of this slide. That is the end of slide number 18G. There are more stuff on molecular, on diatomic molecules, which will be covered in the next few slides.